Them to generate automatically a ROP.
Yes,
Thank you.
exactly. So hi everyone, I'm very happy to be here. And today I will present to you a ROPGenerator. So it's a tool I developed that can automatically build return-oriented programming exploits. So the talk will go as follows. First, a quick reminder about return-oriented programming, so short name ROP. I will show how a ROP attack works, and I will discuss the two major problems that attackers have when they try to use ROP. Then I will talk about ROPGenerator and describe the method that it uses in order to automatically solve those two problems. And eventually I will provide you with some results. So I will compare ROPGenerator to a state-of-the-art tool. And I will also make a quick demo to show how the tool can exploit a vulnerable binary and bypass system protections. So let's get started with return-oriented programming. So how do ROP attack works? Basically, I will show it on a buffer overflow. So when you have a buffer overflow, you can... Excuse me? Thank you. You can override the stack with an input. So what you will do is you will replace the return address of a vulnerable function with a list of gadget addresses. A gadget is a small code snippet that you take in a vulnerable program. So it's a few instructions ending by a return instruction, basically. And by chaining gadgets together, you will have arbitrary code execution on the vulnerable system. So how it works in practice, when you return from the vulnerable function, you jump to the new return address, which is the address of the first gadget. Then you execute the instructions of the first gadget, and when you reach a return, you jump to the next address in the stack, which is the address of the second gadget. So you jump to the second gadget, you execute, you reach a return, then you jump to the third gadget, and so on. And so you can see that by chaining gadgets, so creating what we call a ROP chain, you can execute any sequence of malicious instructions in order to compromise the vulnerable system. So it's a very powerful kind of attack, but when you try to do it, you have two main problems. The first one, we call it gadget search. So you have your vulnerable binary, and you have a set of gadgets that you can use in this binary. The problem is you want to do some operation, like put register 1 in register 2, and you have to find the gadget that does it, that has the right instruction to do it. And you can have thousands of gadgets in a single binary, so you have to look at each of them and see if they can do what you want or not. So it's very time consuming. It's the first problem. The second problem is gadget chaining, and it corresponds to the case where you don't have a single gadget that can do what you want. So you will have to execute several gadgets in order to emulate the operation that you want to do. For example, if you want to put EBX into EAX, you might use a gadget that first moves EBX into EDX, and then another gadget that moves EDX into EAX. So to solve those problems, you already have some tools that exist, actually. You have syntactic tools. Basically, they list all the gadgets that you have in a binary, and then you can make syntactic queries to find gadgets that you think are interesting. They're very fast, but they're also not so powerful because it's difficult to find good gadgets. Then you have semantic tools. They not only list gadgets, but they also analyze their semantic to understand what they do. And then you can provide them with a semantic query, just tell them what you want to do, and they will find the right gadgets. So in practice, for gadget search, finding a single gadget, semantic tools do quite well. So they can be very helpful. But when it comes to gadget chaining, you have a lot of, you don't really have a tool that gives you very practical results in reasonable time, let's say. So that was the motivation to write ROPGenerator, because we wanted a tool that could do gadget search and gadget chaining in an efficient manner. So let's talk about it, ROPGenerator. I will show how it solves both of those problems and briefly talk about the implementation also. So gadget search, find a single gadget that fulfills some semantic requirements. To be able to do gadget search, we decided to represent gadgets as dependency graphs, and then from those graphs, extract the gadget semantics. And then, according to its semantics, we would add entries for this gadget in a like semantic database, so that you can just query the database with a semantic query and get the gadget that matches this query. So here you have an example of a gadget graph. So the gadget is push EBX, then move 0 address ESI, and then pop EAX return. So the nodes of the graph are registers. If you look at ESP register, for instance, you can see that you have several nodes for ESP. So basically you have one node every time you modify a register. So ESP0 at the bottom is the initial value of ESP when you start executing the gadget. And then ESP1 will be the value of ESP after the push, ESP2 after the pop, and ESP3 after the return. The arcs, the dependency arc in the graph represents a dependency between registers. So if you assign register 2 to register 1, you will have an arc, a dependency arc from register 1 to register 2. And this will help us compute the semantics of the gadgets. Also, I didn't mention it, but you have one single node that represents memory, and arcs with labels. They are the memory addresses where you write and read from memory. So how do you compute gadget semantics? In other terms, how do you express how registers have evolved after execution of the gadget? So we're going to take ESP as an example. So you take the last value of ESP, ESP3, and you can see in the graph that it's equal to ESP2 plus 4. So then you will just follow the dependency arcs in the graph, and you replace ESP2 by its dependency, which is ESP1 plus 4. You do the same for ESP1, and then until you reach ESP0. So now you have ESP3 equals ESP0 plus 4, which means that you express the final value of ESP depending on its first value and the initial value. So here you can see that this gadget is incrementing ESP by 4. Let's take an example on EAX because it depends on memory, so it's a little bit more complicated. So you can see in the graph, EAX is equal to memory at address ESP1. This comes from the pop EAX instruction. And what is memory of address ESP1? Well, we will check all the arcs of the dependency arcs of memory, so the write operations, the previous write operations in the memory. And you can see that you wrote 0 in memory as at address ESI 0. So you know that EAX will be equal to 0 if ESP1, the register from which you, the address from which you read, is equal to ESI 0, the address from which you wrote previously. If it's not equal, then you don't know yet what it can be. Then you check the other arc, and you can see that, okay, the other value of EAX can be EBX if ESP1 equals to ESP1, which will always be true, and if ESP1 is different than ESI 0, which means we wrote EBX in the stack, and we didn't overwrite it with the 0 before popping it into EAX. So once you've computed all the semantics for the gadget, you can just add entry for this gadget in the big gadget database. So, for instance, you have the dependency for the instruction pointer, EIP, is equal to memory at address ESP0. So this is from the return instruction, actually. And so you will add an entry in the database for EAP equals to memory ESP. Then you have ESP3 equals to ESP0 plus 4. So you will add an entry in a database for ESP equal ESP plus 4. For EAX, it's a little bit more complicated. You have two possible values. So you will have two entries in the database. You have one entry for EAX equals 0 and one entry for EAX equal EBX. And you also store the associated preconditions. You can do this for the memory. You can do this for every semantic that you computed. And basically, after you did that, you just need to make a semantic query to the database, like give me a gadget that puts EBX into EAX, and you will get this gadget. The next part will be gadget chaining. So now we can do gadget search in an efficient manner, let's say. So we will now do gadget chaining. So to be able to efficiently combine gadgets together, what we will do is we will use the previous result that we had. So we will take all the available gadgets, we will build this big database with gadgets, and then we will use it. And we will use it with a search engine that can look up in this database with semantic queries. And then the search engine has predefined strategies in order to combine gadgets to combine gadgets and emulate operations that it cannot achieve with a single gadget. So I don't want to dig too much into like theory. I think I will just give an example of how simple chaining works. So let's say the user provides a semantic query to the search engine. So here it's please put edx into ebx. So the search engine uses a basic lookup method to look in the database for this semantic requirement. And let's say the database gives no result. So the basic lookup method said, I didn't find any gadget that can do that. So the search engine will try to use one of its strategies. Here, we will try to use an intermediate register. So put edx in some gadget and then transfer this intermediate gadget into ebx. So let's try with EAX. We use the basic lookup method. We query the database, and let's say we find a suitable gadget. Then this gadget is returned to the strategy. And now we have one part, like, okay, EAX into EBX, but first we want EDX into EAX. So again, we do a query to the basic lookup method. We query the database. We get a matching gadget. We return it to the strategy function. Then you have everything you need to build the ROP chain that can put EDX into EBX. So you just reorder the gadgets. If you need to add some paddings because you have some side effects from pop instructions, things like that, you add it. And then you just return the ROP chain to the user. I don't know how much time I have left. I finish? Yeah? Okay. So I will very, very briefly mention the chaining strategies that I have. We can come back to it for the questions. I don't want to spend too much time on it, but basically on the left you have all the basic semantic queries that you can do, and on the right you have how I emulate them with by chaining different gadgets. So I'll skip this part, sorry, because I don't have much time, but we can come back to it later. I implemented those methods, so the graph representation and the search engine in a tool, ROPGenerator. So it's written in Python, and you can find it on GitHub. It's free. The tool can do semantic search. It can chain gadgets, and you have also more advanced exploit strategies, as we will see in the demo. Just before the demo, I want to talk about the results that we got. So I compare ROPGenerator to a state-of-the-art tool, which is called ROPer. So it's the tool that has the most flexible and the richest semantic search features at the moment. And basically, I analyzed the tar program, which is about 17,000 gadgets. And I had a set of semantic queries, and I gave them to each tool, and so if the tool could build a matching ROP chain or not. So you can see that ROPGenerator performed much better than ROPer on queries that involve only transferring register values. I also gave queries manipulating memory, so putting one register, reading or writing from memory. And again, ROPGenerator proved to be much more powerful. I also measured the time consumption. So for binary analysis, so it means like the time you need to get all the gadgets and analyze them. And you can see that ROPGenerator is actually much slower than ROPer, but still like the time needed for the computation is really acceptable. Like 2-3 minutes, you can just get a coffee and come back, and this is done. But I also measured the time that the tools needed to answer a query. Like when you type a semantic query, and how much, what's the time before you get an answer. And actually you got almost immediate answers with the ROPGenerator, while ROPer takes some time to give you a matching gadget or ROP chain. So I think it's the best trade-off because, you can wait for the analysis to be done, but when you sit in front of your computer and start to exploit a program, like you don't want to wait 10, 15 seconds to get an answer. It's nice to have a responsive tool. So now I will demonstrate the tool on a vulnerable program. So I will exploit a binary from ROP. So it's a challenge that is level hard on the site. It's a 64 bytes ELF executable, and it's exploited with system protections activated. So you have ASLR, you have the heap and the stack that are not executable, and you have read-only relocations also. So I will launch the demo now. Files. Okay. So I renamed the challenge here like challenge XX. So we launched the binary, and you can see that it waits for an input, and it gives you the X result from your earphone. So here I try to make the program crash. So I just give it like a very long string, like classical stuff. And you can see that I get a seg fault. So probably it's vulnerable. Okay. So what I will do is I load the binary in a ROPGenerator, and I extract all gadgets and analyze them. So here you can see that actually I fast forwarded the time. The analysis took about 3 minutes. So I create the gadget database and I initialize the semantic search engine. And then you can see that ROPGenerator has 2 modes. So it has the semantic mode. You give a semantic query and it gives you a matching ROP chain. And then you have the exploit mode with the higher level functionalities, let's say. So we will use this mode for the challenge, and we will use the pawn command, which aims at building a full exploit. So we will specify the bad bytes, like the bytes we don't want to be in the exploit because it would truncate our input and you cannot exploit it. We tell the tool that we want the exploit to be written as a Python script. We tell him that to write it in a file, so let's say exploit.py. We will specify the padding length. So I like kind of blurred it not to give the full answer to the challenge. So deliver shellcode is the strategy that we will use. And the address range is the address range that ROPGenerator can use to deliver the payload. Here, it just corresponds to the heap of the program. So you can see that the tool supports, like you can add your own shellcodes in the tool. So here I just added 2 shellcodes from Shellstorm, and then you can use them with this deliver shellcode strategy. So here we will do just the exec binsh classical. So the tool builds, so this is real time, so it takes about one or 2 seconds, and we built an exploit that is 1,000 bytes long, approximately. Now we can exit the tool. It did its work, and we will briefly check what exploit it generated by looking at the Python script. So you have the padding that you requested. Then you have a call to mprotect to make some more memory executable. Then you have a ROP chain that copies the shellcode into the memory. And in the end, you just jump to your shellcode. So I will add one last line in the script just to print the ROP chain. And then we will try to feed it as an input to the vulnerable program and see what happens. So we write it in a file called payload, and then we give it as an input to the challenge. And hopefully we get a shell. Launch it, and you can try the ls command, and you can see that you pop the shell. So this was done in about like less than 5 minutes. You could exploit the full program and bypass the system protections. Where are my slides? I cannot find my slide. See? Okay, I have one last slide, just a quick summary. So what we've seen today in this presentation is, so we described ROP, which is a powerful class of attack, but we saw that you have two main problems when you try to do ROP. It's gadget search and gadget chaining. We saw how ROPGenerator tries to solve those problems by using graph representations for gadgets and custom search engine. And then, we could see that the results were quite promising. It's like more powerful than some state-of-the-art tools, actually all of them. And the time performance is also quite acceptable. And as you can see, it was tested also on real binaries. So there is still a lot of work to do to improve the tool, but I would say it's very promising. Thank you very much. So I think we have time for a few questions.
I think so. Is there any question?
Hey, good stuff. Is there any upper bound for the length of your gadgets?
Sorry?
Is there any upper bound for the length of the gadgets? Do you cut at some point how many instructions one gadget could have, or?
Yeah. I mean, it's like arbitrary, but the user can also define it. You can say the maximum length that you want for your ROP chain, and then the search engine can try to find the shortest ROP chain as possible, for example.
Okay, and then in that sense, does it also keep track about the state of the control register? So can I have chain gadgets with conditional execution, more or less? Let's say I have one gadget which does test EAX, and later on I have a gadget which will do jump not equal, but and then will jump out if the zero flag is set.
The architecture could support it. I can implement it, but it's not implemented yet.
Okay, cool. Thanks.
I would like to know if you have a bound on the size of the code you will generate.
The ROP chain?
Yeah. Do you have is it complete if you say no, it's not possible to build anything for an instruction, one query you want?
I would not say it's Turing complete, but I think it's the best trade-off. I mean, you get really good results. Maybe you could miss some very, very tricky cases. It's true, because the representation is not perfect. I don't use SMT or very powerful solvers like other tools. But usually when you have a ROP chain, I can find it. Yeah.
And second question, what is the complexity? Because you say it's fast, but it's depending on the input.
The input is, you mean the semantic query?
No, the program you're analyzing.
The program you're analyzing. So I didn't test it on 10, 20 megabytes program. So they were about 1 megabyte. So they generate around 40,000 gadgets. Yeah. So it takes about 2 to 3 minutes. We have some idea to speed it up. Basically, pre-compute some generic gadget signatures, and then when you have a gadget that matches, we already have the semantics computed. Yeah.
Okay. Thank you.
Thank you.
One more question.
Hi, so thanks for the presentation. I just wanted to know how many architecture are supported at the moment.
How many?
Architecture. For example, x86 or ARM or MIPS, for example.
How many architectures?
Yeah.
So actually I'm using BARF disassembly platform to analyze gadgets. So it translates them in intermediate representation, which is called Rail. And so far I only exploit Intel, so X 32 and 64 bytes Intel architectures. The ARM support is going to come soon, and then MIPS we will see. We'll see later. Yeah, basically I depend from BARF, which is the platform I use to disassembly the gadget.
Okay, thank you.
There were another question here. No?
Here in the front.
Thanks. Is it long to generate the chain when you don't have a gadget to do the search that you mentioned, trying to find registers?
When you don't find a gadget, and you mean you can iterate forever. I set some bounds actually, but it's even when you don't find the chain, you get quite a fast answer. Yeah. The difficult, when it takes some time, is when you try to optimize the length of the ROP chain, because basically it will do a dichotomic search. Try with, say, a certain length, and then half of it, and then half of it, and half of it, and if you don't find, you will have it's a logarithmic number of tries depending on the length. Yeah, but no, you get quite a quick answer. Yeah.
Still fast.
Mm-hmm.
Good. Thanks.
No more question? Yeah.
Thanks for the presentation. Do you have also a limit in your gadget search on the number of instruction before the rate instruction that you analyze, or do you take all instruction since the last branching instruction?
No. If you take all the instructions, like the whole basic block, you have too many side effects. Usually it's 4 or 5. You can go to 6 instructions, but in practice, I very rarely see a ROP chain where you use gadgets that have 6 instructions. Yeah, and when I do the gadget search, so far I interface with the ROP gadget tool, the famous tool, and it's not maintained anymore. But so I will drop it, and I will use barf instead to find gadgets too by disassembling the binary. But yeah, 5, 6 instructions, it's good for me, I think. Yes. Yeah. Or if you have a jump instruction, then you stop before, right? But yeah, maximum 5 or 6, I think is fine.
Thank you. Yeah, so it's a naive question, but how did you manage to defeat ASLR on your example?
Oh, ASLR is just because you use code that is that you take from the binary. Yeah.
Okay.
Because
it's not a library.
If the binary is not compiled as a position independent executable, you can just reuse the code.
Okay.
Right?
Okay.
I mean, if you have PIE and it's very difficult to do ROP, or you have to use some library that depends on it. Yeah.
So I have a question.
Yes.
Could you combine your approach with SMT solver to make your queries quicker, or to help the user to find the right semantic alternative ROP gadget?
So it's a very good question. Actually, when we started to write the tool, I was trying to use SMT solvers. And it turned out to be not so efficient, because SMT solvers are very powerful, but the drawback is that they turn out to be quite slow also. And the problem is, if you want to combine gadgets and then solve the ROP chain with the solver, you have a combinatory explosion that the computation time just takes too long. It's a shame, because SMT solvers are very powerful. I could try to use it for certain tasks only, but definitely I think the main architecture of the tool should remain this one, with a database that you can quickly query, and not trying to brute force, because other tools, they not exactly, but they in some way they try to brute force the ROP chain, just combine gadgets randomly and see if they solve the ROP chain and see if it does what they want, but you get too much computation. Yeah. The advantages of these approaches is that you already have all all the operations that you know exactly what the gadget does and under what conditions. So then you can very specifically pick the gadgets that you want and combine them together quickly. You don't need to brute force anything.
Let's thank the speaker again.